Good morning, everybody. My name is Silvia Onorato, and I'm a PhD student at Leiden University, working with you now in the Enigma group. And in my work, I focus on spectroscopy of high-redshift quasars. The goal of my project is to place constraints on some parameter of the universe during the epoch ionization. In particular, we're focusing on the fractional neutral hydrogen, the quasar lifetime, and in discovering how did the supermassive black hole grow a redshift higher than 6. For this part of my project, we are focusing on the second one of these questions. And the way we are going to address it is making new proximity zone size measurements that I'm going to describe better in a moment. The starting part of all of this work consisted in building a sample of 45 objects, a redshift between 6.5 and 7.64. All the details about this sample can be found in this paper we have submitted in the archive a couple of months ago. That I strongly encourage you to check it out. And starting from this work, we've built a subsample of objects on which we have performed this kind of analysis. There are basically the red points over there compared with other work from the literature in which the same analysis has also been performed. But what are actually these proximity zones we're talking about? So as we have heard earlier this morning, quasars are very powerful sources, which are able to produce a kind of a bubble of over-ionized AGM around themselves, which imprints enhancing transmission blue word of the Lyman alpha line. The size of this bubble depends on some properties of the quasar, such as its luminosity, its lifetime, and the fractional neutral hydrogen. But unfortunately, it's not directly measurable from the spectrum. So what can we do? First, we predict the unabsorbed quasar continuum using a principal component analysis. And then we apply the definition already provided from Shawifan in 2006, in which we define the proximity zone as the region blue word of the Lyman alpha line until where the red curve in that plot first drops below a level of flux of 10%. And we use it as a proxy to study the bubble and then place constraints on both the fractional neutral hydrogen and the quasar lifetime. So in the sample we have built, we have gotten measurement spanning in this range. And now I'm going to show you a couple of key results and key plots. I want to start with this scatter plot, in which we can appreciate a comparison between the measurement I've gotten and the same measurement from the same quasars from the literature, in which we can see there's a pretty good agreement. And recently, I've also worked a bit with the HQR30 sample, and I've repeated the analysis also on those data, obtaining also in this case a pretty good scatter plot. In this other plot, we can see the distribution of the proximity zone as a function of the luminosity, color-coded with the redshift. And here you can see what is the expected trend, assuming IgM neutral or ionized. And the scatter that we see in this plot in RP for quasars having a similar M1450, we think is probably due to differences in the quasar lifetime. That is something we're going to investigate. This other plot is kind of the other way around. So RP as a function of redshift, color-coded with the luminosity. This is the plots that usually people look at to see if there's an evolution of the RP with the redshift, and usually is not really visible, this evolution. But here I just want to show you that with this sample, we are actually increasing the number of measurements at the very highest redshift. And in my last minutes, I just want to conclude with something that is a very preliminary results. So we are wondering what is actually the probability of getting a certain proximity zone size measurement. And to do so, we want to compare the real data with some results obtained from mock data. So starting from the same set of simulation that Joe and Timo have described before, we have created some mock spectra, and we have repeated on these mock spectra the same kind of analysis performed on the real data. This is just an example for some quasars, a redshift around 6.8 and having magnitude in the J band 20.4. And we have created this mock making some assumptions on both the fractional neutral hydrogen and the quasar lifetime. And this is the distribution that we get. So of course, it's full of open questions. So are these quasars with very small proximity zone actually young quasar? Also, what can we say on the fractional neutral hydrogen? So we don't know yet, but we're going to investigate. So stay tuned and come talk to me if you have more questions. Thank you.
Thank you.